All right, so here's the line in the code where we actually run the optimization. We say, here's my objective function, here's where to start, here's the method to use, here's options like the tolerance for the line search and how many major steps to take. And then we stick something in the result saying what's the label, like the human readable description of the objective function. So we started at 1, 0. We got a derivative or a gradient. We established a bracket. We got a new alpha. And then the next step was not all that far from 1, 0, was it? And then we got a really big bracket and a really big alpha to multiply the gradient by. And then the next step, that's actually fairly different than that. And so we just keep going through, and we'll do a graph later. So that was steepest descent. Now let's take a look at what happened with Newton's method. This is just outputting some stuff. You can see we started at 1, 0, then we were basically at 1, 0, then took a fairly big step in x, maybe not so much in y, and then pretty much stayed there, and then made small changes. Here we're running the optimization for Newton's method, telling it here, do Newton with golden section search, and appending the results of the history to this structure for keeping track of all that stuff. So let's take a look at its output. So again, starting at 1, 0, we get the derivative, and we get the Hessian. And here's the eigenvalues of the Hessian, and we'll talk about that in the next module. And once we use the derivative and the Hessian together, we get the search direction, find a bracket, find an alpha, and just keep going. So let's take a look at what all happened there. So here's our optimal logistic regression. So apparently it does split the difference rather than being all over here or all over there as a local minimum. And let's plot some contours and trajectories of the objective of what happened. So there's our 3D plot of the objective function. There's a heat map of it. Now let's do a contour plot. So we can see the contours are really squished oval-like things. We can't guarantee that they're exactly ovals just from this picture. In fact, they aren't exactly ovals or ellipses. So both methods started here, and steepest descent looked at the gradient, which was perpendicular to a contour running through it, and went this way to begin with, doing bracketing and line search. And Newton's method could kind of detect how squished those ovals were and knew that it should go this way, and it actually kind of went past the optimum and then came back a little bit, and I'll show the animation for that in a little while. So here we can see it with more detail or clarity. Here's the major iterations, and we have kind of a zoom in on that. So you can see the steepest descent is zigzagging. Newton's method just went straight a little bit through the optimum and then came back a little bit. Let's show that animation. So here's steepest descent. So it went that way, line searched its way back this way. LS stands for line search, and then a red dot is for a major iteration. So it line searches this way, and then line searches this way, every other iteration that's doing the zigzag thing. And we just did 10-meter iterations of each method. All right, so it's making some progress, but the optimum is somewhere over here. All right, let's look at what Newton's method did. Here we go. So it started there. Here's doing line searches and also finite difference Hessians. Went way over here, and then let's came back just a little tiny bit. I know it's hard to tell, but we can see that later. And then basically spent the rest of its time just right there at the optimum. Let's look at how the objective function changed with each function evaluation. We can see bracketing and line searching going on here. There's something more subtle there that I'll show in a sec. but it's hard to tell how much better the Newton's method did quickly because the scale is so squished. So here I'm doing a semilog y plot, and I'm subtracting out the true optimum objective function value. So ideally, both of these would approach 0 difference from that true optimum. So you can see steepest descent is decreasing, and you can see all the line searching going on. But here's a puzzle. I said we did 10 major iterations of steepest descent, and this only looks like 5. Can you figure out why we don't see 10 spikes? Take a sec, pause the video if you need to. Well, there is actually a hint here of a little spike and there a little spike. In that zigzagging, it was doing a big step and then a little step and then a big step and then a little step. So I think these are the big steps, and the little steps are so small they're hard to see. And then we can see the first Newton's method iteration got us from 10 to the minus 1 error down to 10 to the minus 4, 10 to the minus 5. Then the next step got us down to 10 to the minus 7. And then the next step down to 10 to the minus 10. And after that, it basically stayed the same, aside from little finite difference derivatives and line searches and stuff. Here's just the major iterations. So even though Newton's method had to do finite differences to evaluate the Hessian, it still made a lot more progress a lot more quickly than steepest descent. But this was just a two-dimensional problem, so the Hessian was just 2 by 2. So maybe the advantage would not be as strong when we had a larger Hessian and more work to do on the Hessian. We can take a quick look at things like the ratio of successive things. If that was constant, a ratio of successive objective function values, if that was constant, we'd be making steady exponential decay kind of progress, but it's not. Here's the angles at each step, but here's the angles at each major iteration. And we can see the steepest descent was doing about 90 degrees each time, 90 to 95. Newton's method basically went nearly straight through the optimum, then came back, so we got like a 180 degree turn, and then after that it was basically just sitting in place. All right, so that's Newton's method versus steepest descent on logistic regression with a very carefully constructed data set, and we saw that it did not get trapped in a local minimum at either one of those clusters or the other one. It kind of split the difference, and that was the optimum thing to do.